Hi everyone, this is Ruthie. In this video I'm going to be doing a proof which claims that the multiplicative group mod p is cyclic for mod prime p. So let's get right to it. Our first lemma will just be that this thing, which is the number of elements in UP, which is just the multiplicative group ZPZ, the number of elements in that group which has order d is equal to the Euler function of d. So where d, actually just right, for all d dividing p minus 1, which is equal to O of p minus O of u p. Because we know that the number of classes or elements in this group is just p minus 1, right? So let's get right to it. So proof or 0. Jesus. Unscripted. So it's equal to the Euler function of t, or it's equal to 0. So first let's just suppose that this thing is non-zero, which means there exists some g in g such that O of g is equal to d. So consider now the cyclic group generated by g of this thing is equal to this thing, which is equal to this thing. Okay, so yeah, that's good. Give me a new page. Okay, and then now consider the polynomial. Consider p of x, which we shall define to be x of t minus 1 for x in u of p. If x0, actually what I'm just going to do here is formally say that the roots of this polynomial, p of x, just are the elements of up of order d. Because if x sub 0 is a root, this would mean that x sub 0 d is congruent to 1 mod p. So it just is like an element of order d. The roots are of this polynomial. We have a theorem by a really famous mathematician that there are at most d roots of p of x. So there are at most d roots of p of x, and O of g is equal to d, and the generators of g have order d, of which there are 5d, many of them. Yay! So this is kind of slick, because we're just we have a theorem that says that the number of generators in any cyclic group, a finite cyclic group, not any cyclic group, is just the Euler function of the order of the generator. So it follows, therefore, that the generators exhaust all elements of order d. So like, since there are at most d roots, and we know that this cyclic group generators have order d, which means that there are d many of them as well. So yeah, there has to be it has to be all of them. So there are no more elements of order d in a group. So yeah, basically the roots of this polynomial just are the generators of the cyclic subgroup, which is cool. And we have proven the claim. The lemma is done. So now we can prove the actual claim. Indeed, 1 is less than or equal to 5 of p of p minus 1, which is less than or equal to p minus 1. This implies there exists g and u of p such that O of g is equal to p minus 1. Therefore, u of p is cyclic. Awesome. So recall that the following lemma works for all divisors of p minus 1, and obviously p minus 1 divides itself. So we get this inequality. I mean, it's not really an inequality. It's actually a mistake. And by theorem, which is just a really characterization of cyclic groups, it's like if G is a cyclic group of order n, if and only if there exists an element in that group which has order n. So it just states that if you have a group of a finite order and you manage to find an element in that group which has the order of that group which it is in, it's cyclic. So from we get from this line here to here because of that theorem. So that's all there is to it, really. Yeah, thanks for watching. Bleh.